Hi, calculus students. These notes are on finding limits algebraically. So before we get into some algebraic examples, I just kind of want to give you the big picture. So we have a bunch of different methods for finding limits. And I'm going to refer to three methods in these notes, one of which we've already done, one of which I'm going to just quickly show you, and then we're going to get into some algebraic examples. So the first method we have for finding limits, which are the intended height of a function, is what we were practicing in class, which is graphically. So I'm going to sketch a quick graph just so we have an example to put into our notes. Just going to sketch a curve with a hole in the middle. Let's call this x value 2. Let's call this y value 3. So then the limit as x goes to 2 of this function I'm calling f of x. Well, how do we find limits graphically? We just kind of look and say as x approaches 2, the x value of 2, I can kind of trace along my graph, y is approaching 3. So even though f is undefined at 2, I can tell that the limit as x goes towards 2 gives me a height, an intended height of 3. So just kind of give us like, how are we doing this? We're just kind of looking and seeing where the height is. I'm calling that look and see. Okay. Another method we're not going to spend too much time on, but I do want you to kind of see that you can do is numerically. So another way we could find limits is by actually plugging in values for x into the function. And the way that works is, say I'm going to give us kind of a weird function. The limit as x goes to 9 of x minus 9 over the square root of x minus 3. And now if I didn't give you a graph and I just gave you this, you might not know exactly what to do here. I don't really know what this graph looks like. I'm not sure what, as x approaches 9, what this is doing. But one thing that I could do is just create a table of values. And think about plugging in x values that are getting closer and closer to 9. So I want to do it on both sides because remember your left and your right hand limits need to match. So I could try like 8.9, 8.99. So that's coming from the negative side of 9. And then I also want to cover some points on the positive side of 9. So that would be like 9.1 and 9.01. And you could use a graphing calculator by putting this function into the graph and looking at the table, or I just did this quickly on Desmos and pulled what the function values are for all these x values. So at 8.9 I got 5.983. At 8.99 I got 5.99. So from the left hand side it looks like it's getting closer to 6. And then I could check the right hand side and do 9.1. I get 6.002. And at 9.01 I get 6.001. So I can kind of tell that as my x values here are getting closer to 9, my y values are getting closer to 6, right? So this is leading me to conclude that my answer here is probably 6. So now one thing to note here is, first of all, this is kind of tedious, right? To plug in all these values and get these weird decimals. So I'm going to just notate that. It's kind of tedious. We're not going to do this too much, but it is an option. And the other thing is it's an estimate. Like it looks like I'm getting closer to 6, but I'm not entirely sure. Okay? So these are two options. And now the third, graphical and numerical, and now the third option is going to be algebraic, which we're going to get into right now. Oh, I put B a second time, but I really want to say C. Okay, algebraically. And by algebraically, I mean we're going to be manipulating the function to find what the limit is. And we'll just say see examples. Okay, so now let's get into some examples. So my first example is the limit as x goes to 3 of x minus 9 over x squared plus 2. Okay, and I want to remind you that the limit is the intended height of the function, the intended height. So a height is a y value. So if this function has a y value, if this function is continuous, I could just try plugging in 3 into this function, see what I get. Because if I get something, if I get an actual number here, then I know that's going to be my limit. That means the limit is the function value. Okay, so our first kind of method, our first step here is always going to be to plug in the value you see here, which I'm going to call like our C value, based off my original definition of a limit back in our previous notes. So step 1, we are plugging in the C value for x. So let's see what happens when we do that in this example. So in this example, I would get 3 minus 9 over 3 squared plus 2. So that would be negative 6 over 9 plus 2, 11. I get an actual number. It's a fraction, but fractions are okay. So basically, what is this telling me? That this is some continuous function at 3 with a function value of negative 6/11. So that's my answer. Okay, so it's not always going to work out this nicely, but this will happen when your function value, or when f of c is the same thing as the limit as x goes to c of f of x. So that's our examples from graphically where we have some continuous function. Okay, now not all of our examples are going to work out this nicely, but this will always be your first step, is to check and see, can I just plug in the c value and get an answer? So my next example is the limit as x goes to 4 of x squared minus 16 over x minus 4. And so I'm going to do my first step where I plug in. I'm going to kind of abbreviate it a little more. So I'm just writing plug in, but we know, what am I talking about? I'm talking about plugging in the number you see as what x is approaching in for the x, and see what happens. So here, what happens is we get 4 squared minus 16 over 4 minus 4, which is 0 over 0, okay? So this is where we're going to need some algebra, because 0 over 0 doesn't mean that the limit is 0. 0 over 0 is not the same as 0. 0 over 0 is this special form called indeterminate form. And there's a couple of indeterminate forms, but this is the main one. And this is telling us that we have some sort of hole in our graph at x equals 4. So the idea is we're going to try to do some algebra to eliminate the hole and figure out what the function is approaching. What height is the function approaching? So step 2 is, I'm going to write look to simplify. This is a little bit vague, so it kind of depends on what type of function we're given. Here we're going to do it by factoring. Because looking at this function, I can already tell I can factor the numerator. So what happens when we do that? So I'm just rewriting the limit. Now I'm going to factor x squared minus 16, that's the same thing as x plus 4 times x minus 4, difference of two squares, all over x minus 4. So now what do I notice? I notice there's an x minus 4 on the top and the bottom, which cancel. And this is now equivalent to the limit as x goes to 4 of just x plus 4. Now something I want to note here is that this function, this rational function here, x squared minus 16 over x minus 4, is not the same as this function x plus 4. Obviously, this is very different than this. But graphically, they end up looking almost the same, right? The rational function goes along the exact same line as x minus 4, except it's going to have a hole in it at the x value of 4, right? So the idea is that if I take this limit, I should get the same answer as if I had taken this limit. They should have the same limit as x goes to 4. Okay, I'm just going to kind of denote that. So bringing over a little arrow, we say these are different functions, but they have the same limit. So continuing on then, my last step is going to be the same as my first step. I'm going to plug into the function again. And now everything's going to work out nicely because the function I'm plugging into is a different function that is defined at 4. So now when I plug in 4 to x plus 4, I get 4 plus 4, which is 8, and that must be the same thing as the limit as x approaches this function. So for the next example, I'm going to write it down. I'm going to ask you to pause the video and see if you can do this. You can try this one on your own, and then you can press play, and then I'm just going to go ahead and solve this problem so you can kind of check and see were you able to do it on your own. If you pause the video, stare at it, have no idea what to do, then don't waste too much time. Press play and take a look at how I got to my answer. But we're going to follow the same steps as example 2, where you plug in, look to simplify, and then plug into the new simplified function. Okay, so this would be the point where you pause, try it out, and then press play. So my first step, I'm plugging in. And what happens when I do that, I'm plugging in -2 in for all the x's in the function. I get -2 squared minus 2 times -2 minus 8 all over -2 squared minus 4. So in the denominator, that's obviously 0. In the numerator, that's 4 plus 8 minus, 4 plus 4 minus 8 is 0. So I get 0 over 0. And whenever I get 0 over 0, that's sending me along to my next step, which is to look to simplify. So it looks like this has a quadratic on the top and the bottom. So I'm going to factor both the top and the bottom. The top is going to factor into x minus 4 and x plus 2. The bottom factors into x minus 2 and x plus 2. And now what can I simplify? There's a x plus 2 that cancels. So now I have the limit as x goes to -2 of x minus 4 over x minus 2. And I'm hoping then that when I plug in -2 to this new function, I'm not going to get 0 over 0 anymore. Now I'm going to get an actual value. Okay, so what happens here is I get -2 minus 4 over -2 minus 2. Oh, I forgot to write, this is step 3, right? Plug in again. And I get negative 6 over negative 4, which I can simplify into 3 over 2 or 1.5, and that would be the limit of this original function as x goes to negative 2. So this is the intended function height. All right, so I'm going to move on to another sheet of paper. I have two more examples for you. They're a little bit different, and these are a little bit more challenging in terms of the algebra that's involved. But we're definitely going to be practicing in class, and this will be less a focus of any limits assessment, but I do want to expose you to it. So this one is the limit as x goes to 0 of 1 over x plus 2 minus 1/2 all over x. So I know this looks potentially a little scary, but we're going to start the same way by plugging in our c value and seeing if it gives us something that is defined. Probably it isn't going to. Let's see. So when I plug in 0 for x, I get 1 over 0 plus 2 minus 1 over 2 all over 0. And how does that simplify? Well, the top part becomes 1/2 minus 1/2, right? So that's just 0 over 0. And once again, I get this indeterminate form, 0 over 0. So that's telling me now I need to do some algebra to try to transform this or simplify this in some way so that when I plug in, I no longer get indeterminate form. Now, when I look at this function, I can't factor here, right? So I'm trying to think, like, what type of algebra might I try to do to simplify? Well, I see a fraction minus another fraction on top, so I'm thinking, well, maybe I should try getting common denominators here, combining these two fractions on top, and maybe that's going to allow something to cancel. That's what I'm hoping. So here we're simplifying by finding a common denominator. So let's see how rusty your algebra skills are on finding common denominators. So this is the limit as x goes to 0 of 1 over x plus 2. I'm going to leave a little bit of space here before putting my subtraction sign because I know I'm going to be multiplying by something. So I see a denominator of x plus 2, a denominator of 2. These two denominators don't have anything in common with each other. They both have a 2, but it's not a factor of 2. So what that means is that to get the common denominator, I just have to multiply each of them by the other denominator. So here I'd multiply top and bottom by 2. And here I'd multiply top and bottom by x plus 2. And I don't need to do anything to the denominator, like the big denominator. I'm just kind of ignoring that for now, and it's going to come into play at the end. So now this is the limit as x goes to 0 of what? Well, in the first fraction up here, I have 2 over 2 times x plus 2. I'm not going to distribute that 2 in right now because I'm just not sure if I need to. I'm going to kind of wait and see what happens. And then with the second one, I should have minus on top x plus 2 over 2 times x plus 2. And then this is all over that x. Slide this over. Okay. So what's the point of getting the common denominators? So that I can actually do the subtraction on top. So this is 2 minus x plus 2. So we want to be careful when we do this because that negative sign gets applied to the x and the 2, but 2 minus 2 is going to be 0. So what I'm going to be left with here is just a negative x on top over the 2 times x plus 2 all over this. There's still that x on the bottom. And something I forgot just now, and I'm glad I forgot it because this is a common thing to forget, is I forgot to write the limit as x goes to 0 in front. It's okay to kind of get a little bit lazy and not write it at each step, but I just kind of want to remind you that it should always be there. So from here, did that really help me? Is this better than what we started with? It is. And the reason why is because on top we have this x, and in our like denominator down here we have this x. And I say those x's cancel because what we have written here is like we're saying this fraction is all divided by x. Well, that's the same thing as saying this fraction, negative x over 2 times x plus 2, is being multiplied by, well, if I'm dividing by x, that's the same as multiplying by 1 over x. And when I write it like that, oh, I forgot my limit again. When I write it like this, now I can more easily see I have a factor of x on the top and a factor of x on the bottom, which means that those x's can cancel. And that's really great because now I have the limit as x goes to 0 of 1 over 2 times x plus 2. And that looks like something that when I plug in 0 to, I'm not going to get an indeterminate form. So my last step now is going to be to plug in again. If you hear that jingling in the background, that's my dog running to see who's at the door. Okay, so plugging in 0 here, we get 1 over 2 times 0 plus 2, which is, oh, you know what? I just realized I forgot this negative sign right here, so I'm just going to carry it over. So we get negative 1/4 as our final answer. Okay, because it is now 22 minutes into this video, I think I'm going to stop there and save another example for class. So you should have 4 examples in your notes. You should have written down everything that I wrote down, along with any questions that might have come up for you. So star any parts of the processes that you are not understanding and make sure you ask about them next time we have class.